The proposed Burstormer has two main parts: enhanced deformable alignment and the image reconstruction. Enhanced deformable alignment is a multi-scale hierarchical module that, at each level, first extracts noise-free local and non-local features with the burst feature attention, performs feature alignment, and finally refines and consolidates features with an additional interaction with the base frame via the proposed reference-based feature enrichment module. It further employs the burst feature fusion unit for merging features by using the back projection and squeeze excitation mechanisms. The aligned burst of features are then passed to the image reconstruction stage. Here, the adaptive burst pooling module transforms the input burst size to constant 8 frames through an average pooling. Finally, no-reference feature enrichment module progressively aggregates and upsamples the burst features to generate the final high-quality image. When capturing an image, we obtain a sampled version of the scene that is limited in quality due to the imaging sensor. Existing approaches in single image processing focus on restoring or enhancing the image using learned priors. While these methods are capable of generating visually appealing images, they often struggle to restore fine details due to the lack of available information. Burst photography offers a natural solution to single-frame processing by capturing multiple images of a scene in quick succession. Also, it is easy to capture the burst image due to smartphone advancement. When capturing image bursts, the movement of the camera or scene objects can lead to alignment problems when merging information from each frame. This can result in undesirable artifacts, such as ghosting and blurring in the final output. Existing methods address these alignment issues through complex explicit feature alignment and deformable convolutions. However, these methods primarily focus on local features at a single level without fully exploring the potential of incorporating global information and multi-scale features. Furthermore, when aggregating features from multiple frames, current approaches often rely on either a early fusion strategy or a rigid fusion mechanism based on the fixed number of frames. The former approach restricts flexible communication between frames, while the latter limits adaptive processing across multiple frames. We propose Burstormer, a novel transformer-based architecture for burst image restoration and enhancement. In comparison to existing works, our approach exploits multi-scale local and non-local features to achieve improved alignment and feature fusion. Our key idea is to enable interframe communication in the burst neighborhoods for information aggregation and progressive fusion while modeling the burst-wide context. In Burstormer, we propose enhanced deformable alignment, EDA, which employs a multi-scale design as shown. Since subpixel shifts among frames are naturally reduced at low spatial resolution, using the multilevel hierarchical architecture provides us with more robust alignment. Therefore, EDA starts feature alignment from the lowest level and progressively passes offsets to upper high-resolution levels to help with the alignment process. EDA has two key components: feature alignment and reference-based feature enrichment. Feature alignment module utilizes a modulated deformable convolution to align features of each burst frame to those of the reference frame. To tackle the complex subpixel shifts among frames, we propose the reference-based feature enrichment module. It enables additional interaction of aligned features with the reference frame features to generate consolidated and refined representations. This interactive feature merging is performed via our burst feature fusion unit. It is built upon the principles of feature back projection and squeeze excitation techniques. Once the burst features are aligned, high-quality image is obtained through the proposed image reconstruction process. Unlike existing approaches, to operate on bursts of arbitrary sizes, we propose an adaptive burst feature pooling mechanism that returns the constant burst size features. As shown, the burst features are concatenated along channel dimension followed by 1D average pooling operation which adaptively pools out the burst features as per the requirement. Next, the pooled burst feature maps pass through the no-reference feature enrichment (NRFE) module. The key idea of the proposed NRFE module is to pair immediate neighborhood frames along feature dimension and fuse them using the proposed burst fusion module. However, doing this would limit the interframe communication to successive frames only. Therefore, we propose cyclic burst sampling that gathers the neighborhood frames in zigzag manner, called here as burst neighborhoods, such that reference frame could interact with the last frame as well via intermediate frames. This cyclic scheme of sampling the burst frames helps in long-range communication without increasing the computational overhead, unlike the existing pseudo-burst technique. Next, the sampled neighborhood features are combined along burst dimension and processed with the proposed burst feature fusion module to integrate the useful information available in multiple frames of the burst sequence. To upscale the burst features, we adapt pixel shuffle such that the information available in burst frames is shuffled to increase the spatial resolution. We evaluate the performance of the proposed Burstormer on 3 different burst image processing tasks such as super resolution on synthetic and real burst images, low-light image enhancement, and denoising on grayscale and color data. We train separate models for different tasks in an end-to-end manner without pre-training any module. All burst frames are handled with shared Burstormer modules for better parameter efficiency. We evaluate the proposed Burstormer on synthetic as well as on real-world datasets for the super resolution scale factor ×4. We train Burstormer with batch size 4 for 300 epochs on synthetic burst dataset. Comparative plot shows that our approach significantly advances the state of the art. When compared to the previous best BIPnet, our Burstormer yields performance gain of 0.9 dB, while having 47% fewer parameters, 80% less flops, and runs 2 times faster. Here are few visual results comparison. Here, table summarizes the quantitative result comparison for grayscale and color burst denoising. Here are few visual results comparison for grayscale and color burst denoising. Here, table summarize the quantitative result comparison for burst low-light image enhancement. Here are few visual results comparison for burst low-light image enhancement. We have released codes and pre-trained models if you would like to try them.